So thank you very much for joining this webinar on understanding quantitative optical gas imaging. My name is Steve Beynon. I'm the Senior Sales Manager for Teledyne FLIR for the optical gas imaging line of business for Europe, Middle East and Africa. And yes, thank you all very much once again for joining. So let's start. So just to give you an overview of what I'll be talking about today is we'll be talking about some of the basics, benefits and fundamentals of optical gas imaging. Of course, what is quantitative optical gas imaging? That's the whole purpose of this webinar. We'll talk about the QL320 device itself, also Q mode by FLIR, a live demonstration of the QL320, which I have in front of me here on my desk. And there'll be some additional information slide at the end with links to tutorials we have online with respect to the quantification tool. And then we'll open it for any questions at the end. So optical gas imaging and FLIR optical gas imaging has been around for a very number of years now, and they're used in many industries, but fundamental the oil and gas industry for methane mitigation and finding hydrocarbon leaks, but also using other industries as well, such as the electrical utilities for sulfur hexafluoride, carbon monoxide, etc. But fundamentally, the technology has been of great benefit for yourselves as users and customers for improving safety and emissions mitigation, enhancing productivity and returning investment, helping you to lower capital on operational costs, and of course reducing business risk as well. So it's been a very substantial technology that's been deployed over a good number of years. So just to go through some key benefits with respect to the FLIR OGI technology. So now we are of course Teledyne FLIR, but formerly FLIR Systems. We released the first commercial optical gas imaging camera back in 2005 in the United States, and then in 2006 in Europe and the rest of the world. And just to go through some key technological benchmarks for OGI over the years. Again, we did the first Class 1 Div 2 camera in 2007, and in 2014 the first fixed mount OGI camera. And then in 2017, the world's first third-party or independently tested and verified ATEX camera, handheld camera. And then in 2019, introducing an uncooled, lower-cost OGI camera specifically for methane detection and mitigation. And again, because the technology has been around for many years now, and it's a very powerful tool, regulatory compliance has certainly looked into this, and OGI has been designated the best system of emissions reduction by the US EPA in 2016, and in Europe before that, in October 2014, under the Industrial Emissions Directive, the refining of mineral oil and gas BREF, the best reference document, actually listed optical gas imaging is one of 3 must-use technologies for leak detection. And then following on from that refining of mineral oil and gas BREF, the chemical wastewater and large combustion plant BREFs followed suit with respect to the same ruling for the refining of mineral oil and gas. So again, optical gas imaging must be used as part of leak detection. More recently, the Oil and Gas Methane Partnership 2.0, the reporting for that is very, very comprehensive, on methane, and optical gas imaging is, very comprehensively written into that reporting, as a technology of great benefit. And as we move on in the evolution of optical gas imaging, it's a very streamlined and efficient detection technology. Based upon our FLIR GF320 camera and technology, it sort of has become really the worldwide unofficial standard, and it really has become, sort of the accepted OGI camera of choice across the world for, many customers such as yourselves, end user, operator owners, service provider companies, etc. And as we evolve the technology into the uncooled side of things, You know, there are options now for continuous monitoring of large emission events, you know, to meet the future demands of your cells. And, you know, obviously, as we, you know, work with that, we'll have continuous OGI, providing situal awareness with artificial intelligence, so you can help determine between, you know, differentiating from what is maybe an event or a real leak or a real fugitive emission. So that's going to be very important for how the technology moves on forward in the future. So just to give you a little bit of science behind optical gas imaging, and you can see here absorption spectra of the common hydrocarbon bonds. So we have ethane, methane, benzene, and propene. And fundamentally, you see that these spectral responses of absorption are sort of overlapping each other. And what we do fundamentally with the OGI camera, we spectrally tune the camera to the, you know, absorption characteristics of these hydrocarbons. And that's one of the key things that allow the optical gas imaging to work in the way that it does. And obviously it will allow you to visualize the plumes. And I just wanted to show you this example here because the different types of plumes are important when it comes to quantification. So on the left, you'll see a plume which we call an absorptive plume. So the apparent temperature of the background is actually higher than the plume or the gas temperature itself. So what you in effect is see a black plume. Now on the right hand side, this is what we call an emissive plume. So the apparent temperature of the background in this case is lower than the plume temperature or the gas temperature itself, and in effect it presents itself as white smoke. And this is actually quite important when it comes to using the quantification tool, because you will need to select whether it is going to be a black plume, absorptive, or white plume, which will be emissive plume. So the OGI triangle, now we're all familiar with the fire triangle. We know that. Take one element of the way, you don't get fire. Very similar thing can be applied to optical gas imaging, you know, specifically for quantification as well. But three main things that you will need to work for an optical gas imaging camera to work. Firstly is that the infrared absorption peak of the gas that you want to look at overlaps with the spectral window of the OGI camera. And this is also known as a response factor. And I shall talk a little bit about response factors as we move on. The second one, and this is again very critical important, that there is sufficient temperature differential between the gas plume and the background itself. In general terms, for the cooled camera technology, and this is what we're specifically talking about today for quantification, minimum delta T of 2 degrees C. Ideally, anything above 2 degrees C is good, and that will help certainly with the technology for visualizing the plume and also for quantification. And then the third one is that there must be a concentration or flow of gas present in the image that is greater than the minimum detection limit of the system. And actually the concentration and the flow of the gas and the direction of the flow of gas is very important as well. So to put this into some sort of visual aspect for you, we have on the left-hand side here, sorry, let's bring up my laser pointer. So this is an example of good delta T and poor delta T. Now, you should be able to see my laser pointer. This is an edge of a brick wall. You can tell it's a brick wall. So this brick wall would have maybe had some solar loading on it, and it's creating a good temperature differential between the background, the brick wall, and the gas plume itself. And then on the right hand side here, you see this is just a chain fence, and in the background this is trees, vegetation, and there's a very poor delta T. So fundamentally the temperature of the background in this scenario here is very similar to the temperature of the gas plume itself. So you can, I don't know how well it's coming across on the webinar, but you can see a little bit of a plume around here, but certainly not as well as what you would see it here. So this is a very, very good example of what is a good delta T and poor delta T. The middle one, so this is what we're looking at of response factor. So we have here one image split into two. We have propane and methane. So you see propane has an RF or response factor of 1. So that is your datum, your baseline, if you like. And you can see that methane has a response factor of approximately 1/3 of that. So in this middle video here, the actual release rate for both of these gases is exactly the same, but the methane appears to be smaller than propane because, of course, methane has a response factor of approximately 1/3 of propane. So again, these response factors are very important when it comes to quantification. And on the right-hand side, this is the presence of gas. Also, what we would call concentration path length. So fundamentally, this is what we want to try and measure. It's this plume, and in this case, that as you can see, the plume is coming out. Ideally, for quantification purposes, it needs to be moving across the image, and I'll show some examples of that. But fundamentally, these are the three main OGI factors, and we have to be mindful of good delta T, the response factor, and the concentration path length when it comes to quantification. So the general principle is that we have two measurements. First one, we have a leak rate measurement in the principle that we extract the plume from the background and then derive a concentration path length measurement at a pixel level, whilst also correcting for delta T, response factor, distance, exit velocity, etc. Then what happens is the aggregate leak intensity across a boundary or signal is where we make the measurement. So this blue circle that you can see here, the plume, when it passes through that blue circle, the blue boundary, that is where the actual measurement is made with respect to mass or volume. And then what we do, we'll compare the signal to empirically derived linear calibration curves that had already preloaded into the algorithmic software of the QL320. And then this will then determine a release rate. The second one is to measure concentration in parts per million per meter. Again, we extract the plume from the background, again derive concentration path length measurement at a pixel level. But in this particular case, you see that we have a square box, an area box. So unlike the mass or volume where the plume is passing through that blue boundary, anything that's contained within that box, within the area of the box, is being used to make a measurement. And in effect, what you will then is report a maximum ppm with a user-defined boundary. And again, when I come to do the live demonstration, I can show you these two examples and the effects of moving things around and making the best measurements possible. So what is QOGI? Fundamentally, quantitative optical gas imaging is the ability to utilize optical gas imaging, specifically the cooled hydrocarbon OGI cameras, combined with an algorithmic solution to quantify gas leaks invisible to the naked eye. So let's look at qualitative and quantitative here. No need to answer the question, but just think within your minds, can you tell which leak rate is higher? Well, they're both exactly the same. So within the OGI camera itself, you have the ability to change level and span and certain thermal settings, which will artificially enhance the visualization of the gas. So it's very important to determine, a qualitative versus a quantitative aspect when we're dealing with quantification. So why QOGI? Well, certainly the traditional, if you like, or the method that's been used for many years, method 21, by either using a TVA, in this example here, a toxic vapor analyzer, or a organic vapor analyzer. Very often in the case of just using that alone, you can actually miss the plume itself. So as you can clearly see in this still image here, we have the methane plume on the left-hand side of the component, and the TVA is coming in at the right-hand side, nowhere near the plume itself. So fundamentally, why QOGI is that you can see the leak. So if you see the leak, you can measure the leak. It's as simple as that. Another great benefit for quantification, or the QOGI tool, is to inspect difficult to measure or difficult to monitor components. So components that you would normally have to maybe get scaffolding to reach, or have some rigging or something like that, it becomes very difficult with the traditional sniffer probe method, because it's almost like a contact method. And I think if I recall going back to the subpart W regulations in the US in 2011 or 12, it was determined that if an individual needed to be elevated more than, I think, 3 or 4 meters from the working surface, they must use OGI to find the leak. Well, that's finding the leak. What about quantification of the leak? Similar thing will apply. So this is where the QOGI tool using the OGI camera becomes very important to be able to inspect these difficult to measure components. And also the accuracy of the QOGI as well, compared to other technologies. Again, method 21, a Concawi study was that took place in 2016. I was actually there when the study was made. And the Concawi, they reported that the QOGI had a 6% sort of error rate compared to a 31% error rate for your traditional method 21. So from an accuracy point of view, the quantification QOGI is proven to be better than the traditional method 21. So let's look at the evolution of the QOGI tool. As I mentioned, that the Concawi test was in 2016. So this was, fundamentally this platform that you see here, the QL100. And this utilized a FLIR SDK to communicate with the camera. But what was needed at the time is that for each camera to be used with the tablet, the camera needs to be calibrated to the QL100 itself. So fundamentally, that you would potentially need to send the camera back to a FLIR service center and have that mapped to the QL100, which wasn't ideal, but certainly it was a tool that really started the process off, and you got measurement for leak rate in mass and volume, and just mass and volume at the time. And then in February 2017, the second generation came along, the Providence QL320. Now, Providence is the company that's developed the algorithms and developed this tool, and Teledyne FLIR, we have an agreement with them. But fundamentally, the second generation tool utilized an Atlas SDK. And by using that Atlas SDK, it enabled that the tablet, the QL320, can be used with any FLIR GF320, GFX320, or GF620 camera in the world without any mapping. So the unit I have here in my desk, I can go to any camera anywhere in the world and it will automatically work. And that was a real big breakthrough for me personally. One of the other things that came on board was the onboard camera calibration, again utilizing the SDK. Is that the reason why the first generation needed to be mapped individually to the camera is because the QL is extrapolating the temperature calibration data from the camera itself. But by using the Atlas SDK, that is done automatically. Again, as the evolution of this product from Providence, was becoming more established. We have an exclusive distribution agreement that all of these units will be supplied and supported through FLIR. And there was also a Q mode that was also supported as well. I shall talk about Q mode in a couple of slides' time. The current generation where we are today with the FLIR QL320 launched in March 2020. We added the ability to measuring concentration in parts per million, per meter, and we refreshed the user interface as well, so it becomes much more user friendly. So the GUI, the graphical user interface, it was adapted, and we also introduced some temperature screening features into the system as well to help the user to determine whether the leak that they're visualizing is something that can be quantified or not. So fundamentally simplifying the whole of the process there, whole of the process down. So what is the QL320? So fundamentally, it is algorithmic software on a ruggedized tablet, and it is an accessory for use with the FLIR GF series cooled cameras, the GF320, the GFX320, and the GF620. And it contains a patented quantitative optical gas imaging method. It will allow you to quantify fugitive emissions in hydrocarbons in either a mass emission rate, volumetric emission rate, or concentration, and can be used for leak detection and repair, looking at tanks, pneumatics, compressors, valves, thief hatches, and many, many more. What do I need to use the QL320? Well, obviously a camera, first and foremost, really. Tripod. Now, this is very, very important because the algorithms for the mass and volume calculation are partially based on movement of the gas. So this is movement of the gas, how the gas is propagating through the image, through the atmosphere. So anything that is moving within the image will have an effect on the results. So if the camera is moving around, then that's not really, really good. We need a stable platform. So tripod is very, very important for the accuracy of the quantification. USB cable as well to connect the tablet to the camera itself. And we also advise in this traceable thermometer, an anemometer, and a measuring device as well for measuring distance, because you need to be able to, input into the camera, input into the system certain object parameters. So there are two ways to use the FLIR QL320. One is the tethered mode, so in fundamentally connecting the camera to the QL320 tablet by a USB cable. And the second one is via Q mode. What is Q mode? So Q mode is fundamentally a setting on the camera which will allow you to make a recording of a leak with all the metadata that can then be transferred to the quantification tool for post-processing analysis. And fundamentally, the advantage is that you no longer need to take the quantification tool into the field. So what you will need to do is input the object parameters, and you can see on the right hand side, this is actually a screenshot from the screen in the camera, and you'll need to input these object parameters so that you can get a sensible result. So let's look at these object parameters that the user needs to input. So at the start, we talked about plume polarity, whether it be an absorptive plume or emissive plume. So you will need to input whether it's a black plume or a white plume. The lens, this is automatically inputted because it's in the camera itself. The user will then need to put in the ambient air temperature, also the distance, what gas it is going to be, what gas is it you're looking at, and what leak type as well, whether it be a point or a diffuse leak, and then also the wind speed. So these are object parameters that the user needs to input into the camera in the Q mode, and then make a recording, and then you fundamentally take that recording from the SD card and put it into the QL320 for further analysis. The important aspect to Q mode is that you can take the camera in the field with its 8x classification, because if you use the tethered mode, what you need to do, of course, is connect the camera to the tablet, and for that connection to take place, you have to unlock the door, the compartment door on the back of the camera by utilizing the tool that we provide, opening that up so you can get access to the USB plug, the USB socket. And by opening that up, you are compromising the 8x. So this is very important to have the Q mode available to you so that you can actually go on site and maintain and have that 8x classification within the camera. So the Q mode results, fundamentally exactly the same results as you would receive if you were to take the QL320 tablet out in the field and connect it to the camera. Again, everything is post-processing. The results that you will have is that you will have a short plume overlay AVI file. So this is the video that you see here on the left-hand side. So this is the plume with the overlay. And you'll also have the raw video AVI file, and then also a results PDF. And what you can do, the beautiful thing about the QL320 is that you can rerun various tests, change some settings at the office, at your desk. And as long as you have a good recording of the plume, then a lot of things can be done post-analysis in a safe environment. And that's a very, very advantageous thing, and I use that quite a lot when I've been out to do trials and demonstrations. It's a very, very good tool. Okay, so let's have a look at a live demonstration. So I'm now just going to transfer to the QL320. And we can run a live demonstration. So this is the interface that you will see, and let's start on the left-hand side, user data. So this is data that the user needs to input into the system. So we have plume polarity, so we have black plume or white plume, you can change that to. The leak type, whether it be a point or diffuse release. Now in this example that you can see, this is a point release. A diffuse release would be maybe something coming from a floating roof storage tank where the seal may has been compromised, and it's more of a diffuse, a wider release. But in this case, it's a point release, so we can select the point. You have the distance to input and temperature to input, the composition, so the options that you have to select for what gas type, methane, propane, ethane, and several other ones that you have there. So we'll keep it methane here. The wind speed. Now, obviously it was recommended to have an anemometer to measure the wind speed, and the options for the wind speed are calm, which is 0 to 1 miles per hour, and then normal, and then high. So what you will do is in effect select one of those. And then we have campaign, which is fundamentally your folder name for where you would like your results to be stored, and then memo is any notes that you would have on there. Now, what I'm going to do, because fundamentally we're in Europe here now, I'm going to go to the right-hand side and you can see units. So first thing I'm going to do is put it into something that I'm much more familiar with, meters, Celsius, and then also the units as well. Okay, so we have different units available, both from a volumetric and a mass flow, and also concentration. What I'm going to do at the moment is leave it in, I'm going to change it to standard liters per minute leak rate. Okay. Now, let's have a look at the top right-hand side of the screen where it says overlays. Now, one of the advantageous things that we have included into this is a delta T overlay. So I've selected this delta T now, and you can see there in the image that there's a red strip. Okay, so red is going to determine that there is insufficient, there is not enough delta T to make a measurement. And just to sort of show an example of that, I'm going to change the plume to a white plume and everything is red, because now it's thinking that it's a different plume and that there is insufficient delta T between the whole of the background, the whole of the scene, and the plume itself. Okay, now we put it back onto a black plume, as which you can clearly see it is. Okay, back to the overlays on the right hand side. So below delta T we have the plume overlay. So this is adding colorization to the gas plume itself. And if we look at the bottom of the video there, you can see it says auto plume. And if I now select that to manual plume, it will give me the ability to alter the sensitivity fundamentally of what we're dealing with. But what I'm going to do for the moment and for the purposes of this demonstration is leave it in auto plume. Then on the right hand side at the bottom we have modes. You see in blue there we're in demo mode at the moment. So when you purchase one of the QL320 units, there will be demos built in so that you can actually go and practice and get familiar with the user functions and using the QL before you go out in field. We have load, which is loading a file that you may have saved, taken a recording from Q mode of the camera, or a recording that you've already made in the field. Okay, and then we have normal mode. Now, normal mode is fundamentally generally a basic user mode. So we have an image here, and finally let's look at the top where it says mask off, add a mask, remove last mask. So I'm going to change that, put mask on. Ooh. Let's go to boundary first, sorry. So to the right hand side where it says overlays, forgive me, I was getting ahead of myself there. We have delta T, which we've set, highlighted, the plume highlighted, and then now what we can do is highlight the boundary. So if you remember the boundary, this blue circle, when the gas plume passes through that blue boundary, that is the point of where it's making a measurement. So right now the units on the right hand side, we're at standard liters per minute. Okay, so this is a mass flow volumetric leak rate, and if we look at the left hand side at the bottom, it says results. I'm going to measure now. Now, as it's taking a measurement, it's doing a sample. What you can see with that circle, it's not only having the gas plume passing through it, but the circle is touching the pipe work, various sort of things at the bottom. Okay, so it saved the result there, or it's showing a result after the sample of 2.3 standard liters per minute. Okay, remember that figure. What I'm going to do now is do a reset, and I'm going to add a mask, because anything that passes through that boundary, touching that boundary, whether it be a reflection or anything, will have an influence on the results. So I am now going to add a mask. So fundamentally what I'm going to do is remove the boundary where it's passing through things that are going to potentially influence the true result and the true accuracy. Okay, I am now going to pressure measure again. We'll do a sample result here, and then we can see the difference in what the result would be. Okay, 1.6 standard liters per minute. Okay, so you can see that there's a difference there, because don't call out because I can't hear you. I think it was 2.3 standard liters per minute before, but because that boundary was passing through, it had an influence on the results itself. Okay, now what I'm going to do next, I'm going to modes on the bottom right hand side, and I'm going to press normal mode to then select expert mode. Now, if you now look at the results at the bottom left, you can see that the results are slightly different. What we're doing now, this is sampling every 10 seconds. And you see the save button is red. What it's doing, every 10 seconds, it is doing a sample. It's making a reference against a standard deviation calculation figure. And then when the results, it determines you have a sensible result, then that save button will actually become green. So it does 10-second samplings, and then it will do 1 minute sampling as well. And I find personally this expert mode it's a very, very good mode, because the nature of the gas plume, is changing all of the time. And you as a user need to determine whether you have a good, sensible result or not. And it's just one of those things where we are dealing with nature in respects, because we're dealing with the wind and various other things as well. And we can only control and mitigate against so much of that. So as you can see now, we're running in expert mode. We've had the 10-second sampling and a minute sampling, saying 1.6 standard liters per minute. You can hit that save button now, and then it will save your recording and save your results. Okay, now what I'm going to do is just to change some other examples here. I'm going to remove the last mask, and I'm going to move on to another. Oh, let me come back to this one here. Again, the masking feature is very, very important, because if you're looking at maybe a cold flaring or a vent or anything like that, you can add a mask also to remove, again, anything that's influencing. So removing the tower, removing the masking from that, so that you get the masking is a very, very good feature that we have on here. So I'm going to move to this example here. And what I'm going to do in this case is change things to a parts per million measurement. So as you can see here now, parts per million measurement, we have this square box, this area box, and anything that is of gas moving or anything within this box is going to have an influence on the results. So at the bottom of the area box, you can see yellow. Okay, that is actually a tag that is moving, and it's having an influence on the results. So if we do another example here, I've done a reset. We're now looking at the sampling 10 seconds. So we will get a result here. And then what I'm going to do is move that box, change the shape of the box, because fundamentally, this parts per million measurement is in effect an equivalence to method 21, your OVA or TVA. And this is what we are, when you're working with those difficult to monitor, difficult to reach, you want to have confidence to that you're comparing it with a known technology that has been around for a number of years, but certainly it will give you the ability, you know, to have some equivalence between the two. Okay, so now we have a result here. Okay, so I'm having a look. So we look at the 10-second sampling 43,700. So what I'm going to do now is move the box in an area that maybe that I would put a sniffer probe anyway, but I want to move it in an area whereby there's going to be minimal influence. So I'm going to do that. Okay. So in effect, if you can imagine this, you know, this is the point where an OVA TVA method 21 sniffer probe would be. Let me go and do a reset, and then let's see what the results we have now. So as this is doing sampling, it's very important to realize, and like many systems, you know, user input is very, very important. User understanding is very important, not only about the technology that they're using, but, you know, what you're looking to measure. And I think you need to have a certain common sense also to work with this tool. But once everything is all in place, it works very, very well indeed. So we should be coming up to a minute sampling right now. I think it was 40,700, the previous one, where they had the large area and with a lot of influence there. So now here you're seeing a much different result, which would be much more realistic to that plume size, or the concentration of the plume, I should say, than what we had before. So that's a very brief demonstration of the tool. And so this is, I'm at my desk here, and I shall prove that because I shall put my camera back on. And then here you can see that. So, you know, this is not linked to anything. This is in the demo mode, and you'll have those demo examples actually on the QL itself. So now I'm going to change back to the presentation. Tips and tricks for using a QL320. As I talked about, stability is a must. Use a tripod, even when using the Q mode, just in the camera itself. I must admit, I have been in, you know, situations and on certain environments. I've been on a concrete platform in a refinery that vibrates. It's a challenging environment to work with anyway, but the ideal thing about the camera is that you can move your position. So that's one of the key things, is make sure that your positioning, make sure your composition, make sure that the gas is sort of passing through left to right across the screen rather than to and from. Avoid any foreign objects within the image as well. So any tags or anything like that, anything that may be moving in the background. Again, when you're making the recording, the better the recording that you make, the better the results you're going to have. Yes, there are tools in the QL320 will help you mitigate against these things, such as the masking tool, which is absolutely fantastic. But you know, it all comes down really at the end of the day is that the recording that you make, okay, the better that is, then the better the results will be. Don't sweat the small stuff. You know, we know that when we talk about fugitive emissions, there are big emitters and there's weepers and seepers. They're really, really small things. Now, there are going to be some emissions, some leaks that you are just not going to be able to get to measure with a QL320. The general rule of thumb is that if you can only see a leak in a camera in the high sensitivity mode of the camera, this frame subtraction technique, if you can only see the leak in HSM, then you're not going to really be able to do a quantification using the quantification tool. Again, following on from that is understanding the technology and the limitations and the best practices. Now, we've got training courses. In a couple of slides, you'll see some, and when you get a recording of this, we've got links for tutorials online to give you guidance, tips and tricks furthermore as well for the successful deployment of this technology. Okay, so again, just to highlight, remove any tags, move them out the way, make sure that the gas plume is moving, across the screen rather than coming towards you or going away. And again, if a leak can only be visualized in high sensitivity mode, that leak is going to be too small for the quantification. So we have a lot of support for this on our website, on our YouTube channel. We have various things, our customer help you can visit to ask questions about this. We've got quick start guide as well. We have some pre-recorded training videos on the quantitative tool as well, the QL320. So these are broken down. I think there's 14 different sort of 3-minute videos that you can view. And again, we've got top 10 questions, FAQs and various things. The one thing that my experience when using this tool, and like anything really at the end of the day, the more you use it, the more experience you gain, and the more experience you gain, the more confidence you have. And fundamentally, it is a very, very good, powerful tool. And with the need, certainly within Europe now, and certainly with the oil and gas methane partnership, this reporting of measurement and reporting and mitigation is vastly important. So thank you very much for your attention. I can now open things out for any questions.